You can get a different type of service.
Yes.
We can
Yesterday, when I left, I went home and I did the calculation to understand why it was.
yeah.
And then suddenly, once it was in front of me, I was like,
It works.
how have I not observed this for all this time? How did I not, how did nobody tell me that this was the case?
The main motivation for this kind of work was that at that time, the only way of looking at entanglement was bipartite concurrence and on qubits.
Yes.
And people coming from condensed matter, these things are not our system.
They are not bipartites.
Yeah, they are not about that. There are no qubits and things like that. And then the natural thing is what is equivalent? And then it turns out that you can make equivalent if instead of focusing on the state space, you focus on the set of observables.
Correct.
That is the whole point.
And
That is the main idea, the main feasibility.
And there is a nice diagrammatic way of saying what it
Oh,
means
really?
to be, well, yes, what it means to be minimal in that, so to have zero in that.
Statement, yeah.
Yeah,
Or to be minimal, that means entanglement.
yes.
We respect that.
And it means so entangled in fact that all of your one system marginals are the maximum in its state.
Yeah, exactly. It is exactly the same.
So you can write it in terms of traces and you can try to figure out whether the GHC states are the only states that work.
That's great. So my question was, in your generalization, if it satisfies exactly the same thing, probably does.
So all the GHC states do satisfy exactly the same thing. Yes. But what I don't know yet is if they are the only ones that satisfy.
Oh, that is a different question. Yeah,
Yes.
that is exactly a different question.
So yesterday I spent some time trying to figure out what the conditions, the diagrammatic conditions are for this to hold. And what I got out of it was
Okay.
it's you get that the states have to have a very special form, which GHC states obviously have all of them, including the non-obedient ones.
Yeah.
But
I know the unitary rotation, so those obviously,
of
those
course,
are unitary
so
system.
those, and the problem is, when I figure out an answers for the bit that I don't know, that is sufficiently general that I can then reason away and conclude that that's the only thing I can do. That I have not yet.
Yeah, and I can give you another more interesting problem if you're interested afterwards.
Oh, yes,
Not
yes, yes.
confused. Do not
In the afternoon, we already have something to finish in terms of nuclear.
Yeah, absolutely.
Because it turns out I did not know that you could do optics and neutrons, and then
Oh, yeah. Very interesting stuff. And the interesting stuff is that there are maybe 10 facilities in the world, and all of them wants to do that.
yeah,
Because you test materials in this way.
yes.
That
So
is a good
last
point.
night I was at dinner with Sean and they were telling me, how did you not know that you can do Newton optics? Like I just never assumed that you could make ring splitters for Newton.
Yeah.
They seem chunky. Maybe they don't go through ring splitters, but I don't think.
Well, you have to build those instruments, and they're highly non-trivial.
Yes.
And then, but they exist already.
That is absolutely not.
Yeah.
So yeah, for the afternoon at topic number 1, for sure. Continue looking at the
That things.
at the foreign level 15, what can be done with that. Like I'm very much. And thank you for these papers.
Yeah, these are, contains the main information. That's it. And there are examples. That's the reason why I brought one of them, because one of them is condensed matter. So please, trying to figure out how to identify phase transition.
Yes.
But there are examples, there are tables with examples, so you can go and check the numbers because all the numbers are computing those things.
Yeah, because that's the thing, these are strictly more general than the.
Oh, yeah, these are more general. There are W states, there are, a few states more general, they are all, computed. I mean, this is just some sort of table that you can check.
Yeah, it's good, but the only ones that I am used to working with are really just the local FUD algebras.
Yeah.
I either using the generalized German basis for the algebra or using the Pauli group basis, but there are obviously if you take super selected systems of any kind, then it's no longer that. You have to use it for
Yeah. And what is physically, what is behind all these tricks? Generalized coherence states. So that's the reason why we have lasers. It's things, and it's not a surprise. I mean, indeed.
Excellent. Plenty, we already have topics lined up for the afternoon. Not important. Not that we ever will. We'll get you audio then, so I can disconnect. Yes, thank you so much for that. This is the test of the microphone. Okay.
Yeah.
And we shall do such things. All right.
Oh, you were weak here.
Good, good. I sent pictures to my parents of the rather dramatic weather, and they were like, "Oh, so you got it's rainy. I see. It's like you got in a week of monsonic rains." And then I sent them a picture this morning of the sky, and they were like, "Hang on, what just happened there? I thought it was raining." Ah. All right, so today I think we start by looking very briefly again at the discarding maps and the measurements, how they take their form, and then we'll, as our last topic, we'll cover causality and purity, which are two useful tricks when reasoning about not necessarily quantum computing, where qubits are actually very close. So yes, there is some notion of causality related to quantum circuits that is useful, and I'll make some remarks about that, but really it's not the physical, it doesn't have the physical relevance that it has in non-locality experiments, as you correctly pointed out yesterday. They say they are tensor products, they're separated, but they're separated by this much. So in order to get anything in the non-locality range, you have to be able to do measurements so fast. And measurements take maybe at 5,000 nanoseconds. That's plenty of time for light to travel from one to the other. So you cannot really do any of these cryptographic, so safe cryptographic algorithms on a single quantum computer. It makes no sense. So maybe that's, again, for when I'm not being recorded, I'll make a comment about that. But still, there is a point to causality in circuits, because it helps you understand which parts of the circuit can affect which outcomes. So for example, you can look at Ansätze for machine learning, quantum machine learning, and you can ask, did I design it right? Like all of these rotations that I put in that seem to be, entangled with stuff, do they really affect the outcome or do they not? Like, did I design my ansatz in such a way that effectively only one of the 30 qubits I measure gives me something useful and the rest are almost in the initial state or a little more than that? And that's a legitimate application of causality as an inference method. So let's just review. I defined this double notation.
which I said I can talk about quantum and classical systems together. So I have some instrument, and this is really just in the calculus. This would be a doubled version of the same map. And in general, I am also allowed to put some discarding here. So you only need discarding on the output, and I'll show you why in a second. You don't really need the maximum limit state, but you can have it if you want. And this kind of looks like you open up the map, and perhaps I should have put, yeah, let's open it up on the top. So you have I star, so the conjugate of the quantum map, of the linear map. And then the quantum system that you discard is traced away. So there's a wire that connects the two sides of this. That is the discarding map. So just for your reference, I define the discarding map for quantum systems to be just the doubled wire with a cap applied to it. So you can imagine that you have the positive part and the negative part, or the positive part and the conjugated part of the state that travel together and then get traced. So if you imagine this in terms of states, for example, this is the trace, the total trace, or the partial trace. So let's start with the total trace. This is a state and its conjugate. So yesterday, I think I had my conjugates below. Today, I have my conjugates above. It doesn't really matter. You can pick whichever looks nicer to you, because they are, the caps and the cups can be sort of swapped around. So the connectivity is the only thing that you really have to care about. So you can rearrange this expression to be psi dagger. You can write it in bracket notation. And then you can observe that this is the same as the trace of the density matrix for your state. If you're used to density matrices, you observe that this is just the total trace. And then you can check that for a larger state, say bipartite state, then this is opening up the state again, but this time only taking away one of the systems. So we now have a bipartite state. One of the two systems has been traced, the other system remains the same. And I can sort of bundle the wires together if I want to make it look nicer. What is this? Well, I have to effectively rearrange this so that it looks like the next picture for the previous case. So I keep the bottom part facing up, or in fact, maybe I should have, yeah, let me rearrange it slightly differently. So this trace is corresponding to saying I have a bra, I have a cat, and then I trace them like that. So I want to reproduce that. I want to reproduce that picture. And that picture for the bipartite case looks like there is a cat on the right, there is a bra on the left, and then part of this goes up and part of it gets traced like that. And now I'm just, again, it's just bookkeeping. And so aside for perhaps I should draw that in gray to remind you that is the bent part for my own, in order to keep things going in one direction. But this is the trace over one of the two systems, which I now have to give names to. So I'm going to call them A and B. So it's the trace over A only, the partial trace, so-called, for the state big psi, which is now bipartite. And because partial traces get really complicated really quickly, it's much easier to arrange them using the diagrammatic calculus and then only open up when you need to. But it's quite hard to write partial traces for big states and keep track of which subsystems were traced. Now the general map has one of these traces, has a quantum part in input and in output. So in input, I'm going to give letters to these. So I'm going to call them A, A, B, C, D, E. So the environment part is the one that's discarded or traced. Then there is a quantum input. I'm going to arrange them in the same order. So there's a quantum input, which goes to both maps. There is a classical input, which also goes to both maps, but is copied with the classical copy. So it's like this. And then there's a quantum output that comes out from both maps. Maybe I'll add the letters at the end. Like so. And there's a classical output that is measured effectively. So really, you don't want to open these things unless you kind of have to, because it becomes fairly crowded. But if you're disciplined, it's better than having to deal with the cross operators of CP maps in general. So the advantage is that you have this package notation that allows you to not worry about the insights until you really have to. Like we did yesterday for the GHZ, for the Mermin argument, we did all of our spider fusions with these packaged doubled things. And only at the end, when we didn't know what else to do, we open it up and apply by algebra to simplify. But at the start, we don't really need to. So it's a way of hiding away, if you will, the complexity that you don't need. And similarly for at the bottom, just for you to have a reference, for the simple case of a CP map, so only quantum stuff, no classical stuff. So this is a CP map, M. You have some quantum input, you have some quantum output, and you have some environment, which you must discard. And this, when you open it up, is the same as having some linear map, and in fact, some isometry, and it's adjoint. If you want it to be CPTP, it has to be in isometry, but we'll discuss that in a second. And you open it up, you trace one bit, you keep the other bit, and that's kind of what you get. And now you might say, okay, but how is this the same as, if you've never seen dilation, how is this the same as a Krauss CPTP map written as Krauss operators? Well, next page. So I can do it in big. Oh, take a CPTP map or a CP map for now, the quantum channel, but without worrying about normalization yet, because we don't need it. And open it up. You open it up, you double it, and you get something like this. And now what you say is, I know that that the identity, or that the cap, if you will, can be rewritten as a sum. It's the sum of the basis vectors of the bras for the basis vectors. It's like the Bell state, but with bras. And now what I get here is a sum over J of a map on the left, a map on the right. And if I define this box here to be VJ, let's say, then I obtain that my map can be written as sum J of VJ on one side and VJ star on the other side. Now, these are the cross operators. How do we see that? We try to apply this map to a state, a general state, okay? So some state rho, which could be mixed, could be pure, we don't know. We don't really know what pure or mixed means yet, but we'll soon get to that. but some state. And if you think of the state as just a density matrix, what you get is the sum of your density matrix with one leg twisted, or yeah, let's do it properly. Density matrix, one leg twisted in front to keep things nice and compositional, Vj on one side, Vj star on the other side, and then I can slide things around, and what I get is the name, or the nice bent way of writing Vj dagger rho Vj. So this is just sum j. It tells you that it's the map that sends rho into sum j Vj rho Vj dagger, which is indeed the expression of completely positive maps in terms of cross operators. So all you have to do to pass from one to the other is to say, I take my trace and I decompose it as a sum of measurement outcomes for some outcome. And indeed, that brings me to the next point, which is that the trace, I can rewrite this part of I can package, if you will, this part of the reasoning, and observe that actually that has physical significance. It tells you that the trace is the sum over any basis. You pick one basis, so some orthonormal basis. Let's call it phi j. J equal 1 dot dot dot. Well, 0 d minus 1. So for a d-dimensional system, whatever it is, and I just take a sum over these basis elements of the effect that corresponds to each of them. So it's really just the result of performing a measurement, and I can actually see that explicitly because measurements have a special property. I can observe that this is the same as measuring in whatever basis I had and summing over the outcomes, the classical outcomes. So this is some basis. I don't know, I'm going to call it phi. And summing over the classical outcomes of this measurement. And indeed, that's just because the measurement has a nice property, and that property is called causality. It's you take a measurement and you discard the outcome. That's the same as not having measured at all and just having discarded the quantum system. So measurements obviously affect the quantum systems, but if you do a demolition measurement and you don't care about the quantum system afterwards, or you just disregard the quantum system altogether, the result for the rest of the world is the same. So not knowing a system or not knowing the system after it's been measured doesn't have any effect on the rest of the world. And this is an idea known as causality. So you have maps, and I should probably just first complete and say for a classical system, it's the same. But typically we consider we just write J for the classical values because it's convenient and avoids issues. And this is effectively the observation that you're marginalizing over some measurement. Now, there's an axiom called causality that says that we are interested in those maps which could have a classical part and could have a quantum. Yeah.
So when you are defining causality in this way, I mean, here you're assuming that there is no entanglement to any. If there is entanglement.
I am. You can still define causality.
I mean, because if you measure some part of your system, it's going to affect the other.
Not if you don't know the outcomes.
Of course, but okay, there is this addition.
Yes, we'll get to yes. Let me define first the diagrammatic bit, and then I'll pick teleportation as the example because it's the sort of canonical. Yes, please. Absolutely. That's So let's start with simple things. Let's start with the axiom in general says that a map, the generic map in completely positive in the completely positive setting, looks like this. Okay, so it has some quantum part, some classical part, some quantum output, some classical output. So quantum input, classical input, quantum output, classical output, and some discarded quantum environment, which gives the mixedness as we shall describe it later. So this is the most general, it's called the quantum instrument. And then you have special cases where you have no inputs, no outputs. So this is sometimes called the quantum instrument, or in general, quantum instrument. And then you have special cases of these maps. You learn to sort of recognize the shapes. You have sort of pure quantum maps, which, well, quantum maps, which can be pure, which can be not pure. You have tests, which are typically not pure, but also have a classical output, something like that. So in a sense, the gradation is you go from just pure things, which are typically just like unitaries or isometries, and then you increase the complexity. And so up to normalization, up to causality, which we'll discuss in a second, because people tend to care about only the causal versions of these maps. They don't like the non-normalized ones, the ones that don't respect causality. So I'm giving you the names for the causal case that we'll discuss shortly. The name for the general case there is no real name, it's just non-normalized or something like that. So these are UMT. So these are just unitaries or isometries. So they're called typically pure quantum channels. And I'm going to say unitaries or isometries. And other people call them pure quantum channels. There is no discarding. Then you you discard an environment. And then you get quantum channels. So CP, TP maps, which are also known as quantum channels. And then you get more generally tests, which have a classical part. So there's a classical measurement outcome of some kind. And the quantum instruments are the more general version, which also has a control, a classical control there. So you can choose the measurement to be made. You have a quantum system that comes in, you choose the measurement or the operation to be performed, you get out of it, some stuff gets discarded, or, well, there's some mixedness, there's some noise added to it, the quantum system itself gets transformed, perhaps it persists, and then you get the measurement outcome at the end. And some examples of these are for just pure maps. You take unitaries. For I said for measurements, there's a few versions of these. There's the decoherence, which doesn't give you any classical outcome. There's the measurement, classical measurement, that gives you a classical outcome. And I guess there's also a control version of the classical measurement that you can make, but in this case is a bit hard to write. I'll write it in a second. So say something like, yeah, fine, why not? Say that you have a controlled Hadamard, classically controlled Hadamard, then you perform your measurement, then another classically controlled Hadamard, something like this, where the outcome comes in, and these Hadamards are controlled by some classical system, like that. And this is an example of a control measurement. So this would be on the right, a controlled Z or X measurement. This would be a Z decoherence. And this would be a Z measurement, a non-demolition Z measurement. Non-demolition Z measurement, just to give you a bit of a zoo, and then you can obviously do the demolition Z measurement, which is where you don't even keep the quantum system at the end. So this is a demolition Z measurement. And you can obviously open these things up. I'm just going to annotate it on the side. So this looks something like that. This looks like that. So you have the quantum part and the classical part, and this one just looks like that. So that's perhaps a fairly general taxonomy of what people use to do measurements in practice. So that's these are some examples. So what's causality? Causality is the requirement for any box, and here I'm just going to drop for a second the doubled and single notation because it doesn't. Yes.
What you're seeing in that scale that you were showing there, that you call demolition Z measurement.
Yeah. It's the same as doing a non-demolition measurement and then discarding the outcome. So it's doing this.
That demolition measurement refers to the fact that there is a conserved quantity. That you're not using in that sense.
No, it's just the case of a measurement where the quantum system doesn't exist afterwards. Yeah. It just sort of
that's demolition.
Yes, yes, not a yes, in the sense of destroying. Yeah. Yeah.
On the same line, where is it the whole diagonal power?
Yeah. So I'll actually try to answer it with the fantastic. We get to the next slide. The causality, and this is causality in arbitrary theories of processes. So not just quantum. So I'm going to temporarily drop the double, single notation. I'm just going to write my boxes as boxes. I do not know what these boxes do. It's some box, some process, P. It has some inputs. It has of some types. It has some outputs. And I say that causality is the requirement that if I discard all outputs, then that's the same as discarding all inputs. And this looks like, so let me maybe give it I1, IN, O1, OM, I1, IN. So it's clear which types they have, but obviously these are diagrams, so the types have to always match. Now, this is the same as saying that P is a causal process. Some people like to say deterministic. In the sense that can be made to happen for sure. Some people, so this is mostly the OPT literature. In the Quantum in Pictures book, this property is called a sure box, in the sense that it can be made to happen for sure. The reason I personally don't like deterministic, even though the Pavia people use it consistently, is that they think of determinism in the sense of intervention. So I can make this happen deterministically, but I live in a world where my theories have both quantum and stochastic processes in them. So to me, deterministic is a function, a stochastic process that is a function. So there's just different academic environments have different needs. We use different words, but they mean the same thing. So this is a causal process. Causal is the word used by the diagrammatic people mostly, who also sometimes say terminal, but I shall avoid that because it only makes sense to category theory. And I'm trying to avoid going into that. So why is this? What does this encode? This encodes the idea that you are looking at knowledge about a process. It's not physical. It's about partial knowledge. So the question, for example, is, I have a Bell state, which is shared between two parties, Alice and Bob. And now I want to ask these two parties are far away, they can only measure, observe their own qubit. So I want to model the local knowledge of the two people. I want to describe the quantum state as they would be able to know it and nothing else. So just what they know locally without being able to talk to each other. And then the local state for A and the local state for B. So for A, I have to take the state and I have to apply a discarding map to the part that A doesn't know. So it's localizing it to A's side. So Alice doesn't know anything about this stuff. And so I need to apply a discarding map to denote that fact. So I'm taking the marginal, if you want. So local state is also known as a marginal. And then we get into the question of how entanglement works. And then there's a local state for Bob, which is Bob doesn't know anything about Alice and he doesn't have access to Alice's state. So the local state for Bob is more something like that. Now we can ask, this is about parties separated in space or parties that don't have access to each other qubits. They can be next to each other, but we still want to model the local knowledge of each party. Then we still have to be able to take partial traces or to discard the side that they don't know. But this, in a sense, this discarding is just lack of knowledge. It's nothing else. Discarding equals ignorance. There is no physical meaning to it. You're not, some people like to say, imagine that you took this and sent it into a black hole. And then some people who are a bit wiser say it will come back out from the black hole in some form, maybe at some point in the future. So actually, technically, the diagram you drew is incorrect. So I think it's a lot safer to just say the application discarding tracing is really just about having access to something or not having access to something. That avoids all of the philosophical implications with how do we interpret the purity of the state of the universe and such interesting questions that we like to ponder. So this is purely about what some parties know and what other parties don't know. And if you think this way, it helps you avoid some pitfalls. More interestingly, this is not just about knowledge in space, it's about knowledge in time as well. So I can take a process that is made of many different boxes, and I can ask, what is the state at one slice of time? What do I know about this process? If I only pick some, so I take a big process that starts with a bunch of states, I'm not even gonna label them, has something applied to the state.
One thing, going back to this question, because this is always a philosophical question.
Of course.
Say, for example, is environment measuring? What we say, no, it's not measuring. So, I mean, this is the knowledge is relative to the observer. I was asking about this problem. So I understand a little bit about the people. I was only ask about the guy who had separate from it. Right, there's a gap between the guys. I didn't do one. I wasn't doing that. I wondered
in a sense, the diagram is the diagram is not the knowledge, is the conviction that this is what happens. Well, I may know things, but I may still want to write them differently. Like I may choose to represent only a partial. Yes. No, not yet. Information about, for example, which parties, which. No, we had not. So it lives together in a broadly consistent stack of different categorical fragments. So people define the syntax for the diagrams, then they define the semantics for the diagrams into some categories, some theory of processes where they want to do calculations. But then if you want to add structures that says, for example, where the observers have been mapped, you have to also add semantics into some space settings. So you have to say my diagrams actually live on top of some space. It depends. For example, okay, before I go to that, let me give you an example here. So imagine that you're trying to model a scenario in space-time where you start with four parties, and I mean, space-time typically goes bottom to top. So let's do that for now. So this is going to be space, and this is going to be time. And I start with four parties. So here is my information about the causality of the parties. And that's what I will care about. They are in some diamond, and I have Alice at the bottom, Bob, Charlie, Diane at the top. Now I want to say, okay, I want to model a process on top of this space-time. How do I do that? Well, I associate to each event in space-time some kind of box. And for now, I will just leave it. And this corresponds to the idea that and here's already a choice I'm making. I'm already saying what I care about is what happens locally at the labs of these four people. And I do not presume that anything happens to the quantum systems in between. And that is a huge assumption, especially if you work in field theory, that is not true. But if you work in quantum information, typically you imagine that up to some sufficiently nice frame of reference where you compensate for the evolution of your qubit in time, then bless you, you get that the system is stable in some sense. And that is a big if. But let's take the simple version. So I say, okay, so I'm going to have some boxes. And these boxes will have some. So for now, I know nothing about these boxes. I just know that they're the processes that are local to my four people. And then they know that these boxes have some inputs and some outputs. In particular, they know that they're sending each other something. And that's knowledge that we have about this protocol. So we know, for example, that there are some types associated, and I'm going to use a different color. So there's alpha, beta, gamma, delta, some types associated to the kind of particles that we say we are sending. And that is a whole other question. If you actually work in the real world with physical systems and you don't presume that you can send the qubit in a nice little box, but that you have some medium that a field propagates into, then it is very much not obvious that you can impose what type follows the wire. And so you might ask, can I make diagrams in such a way that I talk about, say, channels? I'm listening to waves on a channel. That is the state that I receive, and I sort of transmit on a medium without actually being able to localize a particle. And that's more complicated. There is no diagrammatic formalism yet that deals with this, but we're working on that. It's with Nicola. We have been discussing these things for months now, and there are ways to do it, but they are kind of sophisticated physically. For now, people just say, imagine that you're in a lab setup where you can actually send a particle in some way, like a laser beam or cable, something like that. And then in a sense, we know that Charlie's lab has to have, they all have to take something in and maybe get something out. So Alice has to certainly get two things out, Bob, one in, one out. And the types of the wire are determined by our knowledge of the channels that connect them. So there's a beta output for Alice and a beta input for Charlie. There's an alpha output for Alice and an alpha input for Bob. There's a gamma output for Bob and a gamma input for Diane. And there's a delta output for Charlie and a delta input for Diane. So we can label the boxes with the names of their owners, just for clarity for now. And we say, okay, this is the information we have, and now we believe we live in a space-time that is definite. And to me, that is a huge assumption, because my entire recent field of research has been indefinite causal order, where you want to talk about diagrams where you don't know the order of the parties. So that's its own kind of worms, but we'll ignore that for a second. And we say, okay, now that we have all this information, in order to get the diagram, what we have to do to get not really a diagram, as in we get a diagram, but it doesn't give us a full specification. And that will speak to the, does each party have one box? In a sense, yes, in a sense, no. And so we can start writing the big boxes. So the wiring, the local information about what the parties do in their labs, plus the information about the systems, how the events are connected, so how their inputs and outputs are sent to each other, the causal structure of the diagram, allow you to glue together the boxes in a nice way. And you get this, and it seems all nice and trivial, but it turns out it is treacherous and interesting, because now we can do some nasty stuff. So first things first, types must absolutely check, and that's okay. But then I might want to also say, actually, I know that these systems evolve in time, and so I'm going to make sure that I incorporate that. So for example, I could say, okay, this is my diagram now, but I know that actually those wires are not really wires. There is a little box that tells me how the system evolves in time. So I can say I add information to my space-time, and I say that I know the duration of these flights. I know the length of the path, like the proper time for the path from A to B, the proper time for the path from A to C, time from B to D, time from C to D. And now I have additional information, and I can use that additional information, and I can incorporate it in my diagram by saying, I want to also add the time evolution of my systems, and I want that to be something which takes into account the evolution for over time. And I want it to be parametric over, again, this, if you look at this shape for now is purely parametric on the data that I had on the left. It doesn't have any specification. It's a blueprint. It says I will have a box for Diane, a box for Bob. I will have a wire, and the endpoints are going to be labeled by this type. But it's fully dependent on what is on the left. All the information on the left is what I need. And so I can make these boxes, and I can say, for example, that this box here is the evolution, so the unitary that evolves, the system delta over the time. Let me use colors so that it's a bit catchier. It's the unitary or non-unitary, like dissipative if you want, evolution for the system delta over the proper time that it takes to go from Charlie to Diane. So you can be very detailed in this. People tend not to care, mostly because in the diagram, you can just take that and absorb it into the box for Diane. So you can say, actually, I make it so that the box by Diane has each box has the time evolution, incorporates the time evolution from the previous party. But if you want to be sort of fully explicit about what you're drawing, and you want to communicate, because diagrams are both a medium for reasoning, but they're also a communication tool. You want to communicate to the other party that you are considering the case where the system evolves and that is not being compensated, and you want to explicitly do that as part of the calculation, that want to add a phase that depends on time, then that is one way to do it. You just put it in the wire in between. And of course, you could say, I'm not entirely convinced by your assumption that these systems don't touch in any way, and you could have entangling evolution, and you can do many things. But I'm going to go back to the simple case, and I'm going to now fill it in. So I now want to say, that was the plan for what I want to do, but I did not in any way say how it works. And so I start filling it in by saying, first things first, they each have, typically in these experiments, they each have some control. They typically can do some stuff. They have an operation or a button or a lever they can press, and that does different things. And then they get some outcome they can record, because otherwise this is not an experiment. I am of the camp that if you don't get classical information about something, you don't know it. Yes. I'll get it. I'm going to, that's why I said this is the very boring vanilla case where the order is causal. And then at some point, we're going to have to face the fact that the world might have closed time-like curves, and how do we do with that? How do you? And that gives me the opportunity to talk about Deutsch's model, I guess. But now, for now, let's just say these boxes have something more. These boxes have inputs, classical inputs and classical outputs that these parties, let's say like 0, 1, 0, 1, something like that. These people can make interventions. They can change, they have free will of a sort, maybe, we don't know. Presumably they have free will and they can do stuff. And I will like to believe that. And so now we have these boxes. There's some classical wires. There's some that are local to the parties. But as long as it's just bookkeeping, how you can draw them to the top, you can draw them to the bottom, as long as you remember where the endpoints of the wires are. There's no big rule, right? You can, when you start drawing these complicated diagrams with lots of sort of local inputs and outputs, you don't want to have wires that go all the way up and down. Sometimes we have diagrams with 10, 20 boxes. It gets really crowded. So just keep them local and remember that this is the input for Charlie, this is the output for Charlie, this is the input for Diane, and so on and so forth. And now I can also start filling in these boxes. And so I can say, well, so Alice's input, Alice doesn't do anything in her input. So her input is actually just discarded. And what Alice does is take, I don't know, she takes a state and measures it in the Z basis, and the Z basis measurement is her outcome, and then she copies it and sends it to copies to some parties, something like that. And so how do I represent that specification? So let's say that my state is some state on the equator. Then I measure it in the Z basis and I copy it, and the measurement outcome is what I use as my outcome, something like this. And this is the recipe for what Alice does. So this is the concrete specification. And in a sense, so now there are multiple levels of boxes. There's the box that says Alice's plan. This is the shape of what Alice does. And then there's a box that says Alice, what actually happens inside. So there's the outer shape, which says Alice chooses some inputs in some finite set, or infinite set for the matter, has some outputs that she gets locally. That's her part of the experiment. Then there's some stuff that comes out of her machine that she sends to Bob and Charlie. And now I've told you the type of that stuff. Maybe I said those are qubits, but I didn't say anything about how the implementation works. And so some people care about the properties of these processes without knowing the inside, just knowing the causal structure, the inputs and outputs. So you just stare at this, you get a probability distribution on outputs conditional to inputs. So you get something like probability of the outputs conditional to all the inputs. And then you study the causality of that. You study how, is it compatible with the order that I declared? Is it quantum? Is it non-local? And this is called device independent. So it's a device independent setting. In fact, if you don't even know the theory, it could also be a theory independent setting. So you might just say, I have a probability distribution. I do not know how I got this, but I got this. And now tell me stuff. And for those who are not in this particular field, just so you know, you could ask something like, I have a probability distribution between two parties. They have two inputs and two outputs. And I observe the following thing. In fact, let me first draw the process. I believe that there is a process that has kind of like this shape. There's Alice and there's Bob, and there's some state unnamed share between them. And we don't know what the stuff is. We just know that there's Alice and Bob and there's some state, and we don't know what they do. We have no idea. All we know about this setup is that they have a binary input each and a binary output each. And we don't care what the inside of the box is. All we know, we don't even know if this is quantum or classical or maybe made by aliens. But what we know is that they can, when they are space-like separated, so they can be very far away from each other, and they can do this simultaneously. And what they manage to obtain is a distribution that looks like this, where their bits are correlated in such a fashion. So they are the probability, and effectively the probability of getting output for Alice and Bob, given the input for Alice and Bob, is defined to be, and this is kind of a classic example, is defined to be 1/2 or 0. It's 1/2 if OA XOR OB is IA times IB and 0 otherwise. And now this example is called a PR box. And it is the classic example of a way too correlated process to be realized in quantum theory. So these kind of correlations they're maximal, they are well beyond what quantum theory allows. And the point is that, of course, you can make a process between two parties that does that if they can talk to each other, like if the boxes can send signals. But if you put the parties far away and you presume that relativity isn't broken, if it's broken, then we don't talk about non-locality, there's no non-locality. But if you put them far away and they produce this thing for you consistently, not just once, not as a fluke, then there's something wrong about the universe. And then we didn't know some stuff, and this is bad. But this is an example of a device-independent setup where you say, I have some boxes, they satisfy some causal order. I just don't know what theory they're in. I just don't know what they look like inside. And then the good question is there a process theory that realizes this? And the answer is yes, there is one. It's a bit odd, but there is one. And the process theory that realizes it is called box world. And it is very weird. But so I'm not going to go into that. Yeah.
There is an assumption that you're making. There is some sort of tensor product structure between A and B.
There is, in this case. That's part of the theory. The theory has a specific choice of tensor product.
Yeah.
If you don't have that, then you cannot write.
It sounds classically reasonable, but
it's
an assumption.
So interestingly, you can, for most of these theories, and there's a complete aside, for most of these theories, you can actually presume that the tensor product is that of real vector spaces, and that your connecting wires is contraction of real vector tensors, because most of these theories can be embedded in real vector spaces. In fact, I think all of the ones that I'm aware of, the things that people would call generalized probabilistic theories or operational probabilistic theories, to be more precise, they can all be embedded into some real vector space. Typically finite dimensional, that's usually a requirement for theories. So quantum theory is the typical example. You can always embed quantum theory in real vector spaces by taking the basis for the space of Hamiltonians or self-adjoint operators. So a basis for the space of density matrices, and that's enough, because now you have that density matrices are real vectors, and you have that CP maps are matrices that map real vectors to real vectors, and all you have to know is how they operate on the basis of observables. So for qubits in the XYZ basis, for qubits, I don't know, in the German in the basis of German matrices, or in general in the basis associated to the polygroup. There are plenty of options there. But you can always make these theories real, and so you can say there would be a tensor product, and that is kind of complicated, but I obviate to the issue of what the tensor product is by saying, when I write the diagram, I'm really writing it in real vector spaces. And then the question, what is the tensor product, becomes, what are the bipartite states, which is a slightly it is technically slightly nicer, I think, because to someone saying, tell me what the tensor product operation does is a bit stronger than saying, just tell me what I can do in a bipartite setting. It seems a bit closer to sort of operational experience to say, which processes can I do? Rather than there's space here, they're not in the same universe, and now I want to put them in the same universe. How do I join the two systems? But it's sort of a, in a sense, one is the operational perspective on physics, which says I care about the processes locally, how they combine, how they become bigger and bigger. And I presume that I have such control over the universe that I can do things local to a place to some extent. And then there's the large Hilbert space view of the universe where you say, yeah, no, that's an illusion. It's just actually there's stuff. And you're lucky if you can do it kind of confined, but you have the question, what if I have two patches of universe that didn't talk to each other, and now I somehow merge them, and I want to sort of glue them together? What does that gluing operation look like? And that becomes, how do I write a tensor product for the space of global states? So that's...
The reason I'm asking is you mentioned that A and B are two electrons.
Mm-hmm.
Yeah.
When you say electrons, do you mean...
As an entity, these are two electrons. I have a piece of matter.
As a okay, yeah, but a piece of matter has many degrees of freedom. It's like
exactly. You have a piece of matter that has a few degrees of freedom, interferometer or
Yeah.
whatever that has a few degrees of freedom. Because indeed, this is about knowledge. Okay? So, but I know I am an observer, and I know that A is one electron, B one half fermion, and I know B is an electron, B one fermion. At this moment, I cannot make that assumption, because I know that if I were to put A and B, and they are together, because they are in the piece of matter, and observer, I'm seeing they are together. I know that if I move these boxes like that, it's not the same as if I move these boxes like that. Okay, and that operation is not in the tensor product.
That is because you are interpreting the positioning of the boxes as the spatial positioning of the corresponding objects.
So it's a physical process.
Correct.
So I'm in the lab, and I want to do, there are ways out.
Yeah, you can just say it's the information and the position. If you do this operation, what you're doing is a global entangling operation on the field in between, and then you sort of save yourself.
No, but these are firm. So now that these are, both, I mean, it's different.
Okay.
Okay, so it's subtle. I mean,
oh, it is
about knowledge.
Oh yeah. Oh yeah. But for example, if you say there is you can think you have the state of these two electrons. Let me call them E1 and E2. And you can think that you want to have a diagrammatic setting in which doing this means swapping them in space, maybe in 2+1. Okay, so let's say 2+1. Or you can have a diagrammatic setting in which you have the two electrons, and the operation of swapping them in space is some box. That's an entangling box that deals with the swap, the fermionic swap problem, as they call it. And indeed, there's a calculus, which is called the ZW calculus, where they denote this operation by a special swap. So they sort of package it. This would be the swap in space. So I'm gonna put some space behind it just to make it kind of snazzy. And then you can capture it by saying, actually, my swap is not really the swap of the monoidal category. It's a different operation that kind of looks like a swap, behaves like swap in many ways, but incorporates the minus sign if I try to flip it. And then they denote it perhaps something like this. And then the property becomes that this interacts with the informational swap by encoding the necessary phase. And there you are, yeah, aside from the clever notation that kind of looks like a swap, but isn't a swap, this is not really, I mean, the notation is clever and all, but this is a box that takes two things in and gets you two things out, no matter what the picture makes you think. While the swap is purely an informational procedure. So in a sense, swapping the two electrons, so this would be in space, and this has problems, and you cannot purely interpreted as the tensor product of real Hilbert spaces anymore, or real vector space anymore. That's true, because you have the super selection rule of super vector spaces. But instead, you can think of it as just the tensor information about the two electrons. So this is just informationally, and there's no problem there. That's just saying it's a relabeling. I'm relabeling electron 1 to be electron 2 and electron 2 to be electron 1, which to us doing practical experiments seems an obvious thing. You just say, yeah, okay, I call that 1, I call that 2. Now it's convenient to call that red and call that blue. It's okay. It's fine. But in a sense, the swap in this real setting is more like that. It's more of a just exchange labels. Move one here for convenience. You don't even need the swaps. All you need to know is what goes where, and that's it. The swaps is purely for drawing purposes. It doesn't have physical meaning. There's instead categories where it does have physical meaning. So you work in the category of super vector spaces, super selected quantum systems. And in that category, you can impose super selection rules, such as the even odd sectors. And
sometimes, let me tell you why I'm asking this question.
Mm-hmm.
Because, I mean, this idea of certification is very deep. It's a very deep idea.
Mm-hmm.
The device independence certification, quantum certification,
Mm-hmm. It is.
And I think
it's very hard.
This is something that will become more and more and more used in labs, experiments, real experiments.
I 100% agree.
So part of the thing is that we invent always theories, theoretical physics, we invent new particles and new things. Then the question is, how do you falsify that your particles are what you think they are? Okay, and you want to have minimal assumption.
Fair enough. Yeah. So you want to do effectively a device independent, and
exactly.
Yeah, but you want to
device independent test.
Yes, but you want to be theory dependent still, like many. Okay.
Minimal.
Then you want to be fully theory independent, fully device independent. You don't even want to know whether PR boxes exist or not, because to be fair, yeah, if you're at the frontier of physics, you don't know that quantum theory is right.
Exactly.
Correct. That's true.
So this question emerged because of this existence of Majorana Fermi.
Yes.
Do Majorana Fermis exist or not?
Correct.
Okay, and these kind of ideas are really crucial and important to address this question.
Indeed. And we have this entire stream of work on whether you can certify, for example, because you might be looking for new particles, but you might also be looking for new spacetimes. Relativity might be incorrect. In fact, we know relativity must be incorrect in some form because it doesn't play well with the.
Well, if you come from quantum mechanics, you say that. If you come from you say yeah.
I trust more the stuff that I see here than the stuff that's out there. But yes, of course, there's this big debate as to one is right, one is wrong. Of course, both will be wrong in some sense, because you look at quantum field theory and you stare at the way quantum field theory is defined, and it very explicitly assumes that space is kind of flat and nice. And if you want to make it not flat, then you are clashing against the basic assumption of these representations that give you the particles. And if you look at relativity, it presumes that space is well-defined and pointy and everything. And if you go into indefinite causal order, you start asking questions such as, okay, what if I am really careful with how my information spreads, and I manage to put a particle in a superposition of there, and the particle is heavy enough? It's a black hole. I mean, that's crazy, but I'm not kidding. This used to be one of the running examples in the early days. Like, what if I take a black hole that could be there, and then I control its position with a plus state? It's interesting theoretical questions, but spacetime will get deformed, and it will not be pointy. It will not have well-defined points anymore. It will be something else. And so, yeah, you have to be able to determine what's explainable and what's not explainable. And that is the whole ethos of the device independent setting. Correct. So let me just wrap up here. You can, and then we can continue this in the afternoon. But just to have a complete set of slides, you can, for example, perform some control measurements in basis, and something like this. And then perhaps Diane doesn't do anything with her input again and simply measures correlates the two qubits and measures them in some correlated basis. Okay, so measures applies a C naught and measures one of the two parts and discards the other, something like that. So the idea being that these boxes are a definition of what the local patches of spacetimes do, and then you connect them in some way, and that gives you some kind of processes out of it. So at the end, you are able to get the classical probabilities out of this process by gluing together local operations that your parties have done. And since we got into this field, let me pick a paper. And I promise that I'm not doing this out of self-advertisement. It's just, it so happens that I like this stuff. So you go a bit far in a very long paper to look at pictures that might be interesting. And I think the pictures are a bit later. Yes, pictures. I want this, yes. So now presume that you don't know that space-time is fixed, that you live in a world at the edge of quantum gravity and you can do some snazzy new stuff. And you have four agents, all of them acting locally. They start by sharing a Bell state at the bottom and a plus state at the bottom. Here, solid is quantum and dashed is classical because drawing doubled wires is too much of an effort. So there's a Bell state that's shared between the three people on the left and Diane on the right, and there's a plus state. And the big red box is a patch of space. It's an exotic patch of space-time where we don't really know what the order of Alice and Bob is. We have no idea. It is controlled by the first part of the Bell state. So effectively, there's two qubits, they're entangled. The qubit on the right goes to Diane. The qubit on the left goes into this patch of space-time. And what it does is it determines the order of Alice and Bob. So if the qubit is in the 0 state, Alice goes before Bob. If the qubit is in the 1 state, Bob goes before Alice. And if it's in another state, it's a superposition of the two in a well-defined sense. And locally, Alice and Bob are in this weird exotic patch of space-time, but locally in their little spaceship, they're well sealed and their world is classical and they can do classical stuff. And they have an input, they have an output, and what they do is they do the same thing. They measure what they got. They measure what they get from the other party in the X basis. They take their input, they encode it in the X basis, and they send it forward. And so we start with the plus state. If Alice goes before Bob, Alice gets the plus state, measures it, encodes her input in the X basis, forwards it to Bob. Bob measures that, encodes his input in the X basis, and forwards it out of the patch of spacetime where it gets discarded. That's the discarding map. Nobody looks at what comes out. We don't care. And if Bob comes before Alice, then the plus state goes to Bob first, who measures it. Then he encodes his stuff. The qubit that he sends out goes to Alice. She measures it, then she encodes her stuff, and the qubit goes out of the patch of spacetime and is lost. And what comes out of the patch of spacetime is the control system, is the system that entangled their order. So there's this qubit, which was half of a Bell state, which determined their causal order. So imagine that it was the position of the black hole that sort of twisted their relative causal order so that one came before the other. And then it comes out, this qubit degree of freedom is available to someone else at the end. Charlie applies a control rotation and measures it in the Z basis. And on the, yeah.
When the entangled particles that range can be bonds.
Yeah, Alice and Bob, both of them are in there. Nobody is. It's the qubit that comes in. There is no determination. That qubit, the left of the Bell state, is the thing that controls the relative order, but it could be entangled.
But I mean, this looks like the Maxwell Demon. It's something like that. You have 4 agents there.
Yeah.
So now, I mean, that Maxwell Demon is determining
No,
A and B,
no,
whether it's A first or B.
no, that's the point.
Cow.
I know, that's the point.
Very much cow.
That's what people want to understand. They want to understand whether there is a way to device independently certify that the order of Alice and Bob is indefinite, that there is no way to, you can ask, okay, can you ask? Then you look at this scenario, you imagine that this makes sense. I mean, who cares? Maybe there is an explanation, maybe there isn't. We look at it. We look at the outcomes that come, the inputs and the outputs, they give us a probability distribution. Okay, it looks like this. It's for some choice of angles. That's a heat map of the probability distribution because it's too many numbers. It doesn't really get very informative if you look at the numbers, but the heat map tells you that there's some structure to this. And now you ask, certainly this particular indefinite causal order where Alice and Bob, I don't know where they are, that supports my observation. So I know for sure that Diane is space-like separated, and the no signaling is there in the empirical model. The empirical model is the probability distribution for reference. So I know that that's consistent with Diane being separated, and it's consistent with Charlie coming after Alice and Bob. So let's say the outputs of Alice and Bob jointly don't depend on the input of Diane, and they don't depend on the input of Charlie. So causally, and this afternoon I'm going to continue on this causality, but it was just to give you some food for thought, and then I'll revisit this. I know that Alice and Bob are sort of before Charlie, and that these 3 parties are far away from Diane. That's consistent with my observations. So now I ask, can I consistently explain what I see with one of these 2 orders? Can I consistently explain with there is some Maxwell's demon who picks the causal order between Alice and Bob, and sometimes Alice is before Bob, sometimes Bob is before Alice, but if I knew the mind of the demon, I'd be able to tell. Yeah, and the answer is you can, with some effort, you can define a framework where you can compute the maximal compatible fraction, and you discover that you can explain about 31.6% of this with one order, 31.6% with the other order, and the rest is unexplainable. And jointly, this is actually the absolutely fascinating part, that if you look at the so-called causally separable fraction, which is the amount that you can explain. Imagine that there's someone who decides the definite causal order. It goes for some angles over the entire landscape of angles that Charlie and Diane can use in their control rotation. So that parameter decides how much of this experiment is explainable. And it turns out that for a large plateau of stuff, it's fully classically explainable, but there are values where it's about a bit more than 50% explainable. And that in itself is interesting. What's more interesting is that it coincides exactly with the local fraction of the Bell experiment, of the measurements that you're making on the Bell state. So if you take just the Bell state and you do measurements with the angles that Charlie and Diane, the 2 people who measure the control system and the entangled qubit, and you ask what is the amount of that particular correlation that can be explained classically, it coincides with the causally separable fraction. It's identical. So it is the same. It is the non-locality of the state when you plug it into this weird exotic space-time determines the impossibility of explaining the causal order classically. And this was a new result. And you can redo this with other states. It's not actually a fluke of the Bell state. You can do it with a GHG state and 3 parties, and you get again the same result, but a bit more disturbed because there's some issues with the entanglement.
Take a state that is a W state, something that is not maximal.
It still gives you
the same fraction related to the state that
it's not identical. It gets, for the Bell state, it's very close. There is a way of making it exactly the same. For GHG state, it becomes a bit more disturbed. You can see that it's not exactly the same. Now it's different. But yeah, for all or any entangled state is non-local in some way, and it's the non-locality that makes the causal order indefinite. So yeah, to some extent, you always get some indefinite causal order from non-locality arguments. In fact, there is a way of constructing them exactly. You just use the contextual outcomes from the parties and use that to control the causal order. That also works. Yeah.
Except that part, the indefinite parts. All other parts can be broken. Can be embedded in the
Yeah.
Right. So, and do you actually have any idea about how? Is there any way that you can sort of take a statement that response to the indefinite parts shouldn't be too large or anything like that?
Not from this particular perspective, because it's purely information theory. So you don't even know what that, I mean, you know what that looks like as a process. You can write down the super map that does it. So it's a map that takes two CP maps, and this afternoon I'll continue on this, but takes two CP maps and gives you a new CP map. There's a way of expressing it. It's called the quantum switch, but it doesn't say anything about the physicality of it. Nobody even knows how to start realizing this. There's interferometric experiments that realize the quantum switch, but of course what they call space-time events are not really events. They are sort of events in the mind of the observer. Like the photon came into this, the photon passes through the box is not a space-time event. Is the box at this time is a space-time event. And so if you try to do the diagram of the interferometric experiment, you discover that there's actually, where they say there's two events, actually there's four events. There's the event, the photon passes in one and the vacuum passes in the other, and vice versa. So there's four of them. You have to take 2 points of space at 2 times in order to reconstruct it. But they collapse it. They look at, if you will, at a certain slanted subspace of the super selected space, and they just say, if we imagine that the event is the photon enters the box, the photons enter the instrument, then we can realize indefinite causal order. But that's a stretch. That, I mean, without any, actually, no, it is a stretch, period. Why do I have to discount this? It's true. It's but it's because these experiments are purely doing a simulation of the indefinite causal order. They're not actually probing whether you can twist space-time, put it in superposition to create indefinite causal order. That would be Nobel Prize stuff. That's not, I mean, these experiments are really cool, but saying I managed to demonstrate that I can, with some entangled state, put two masses in superposition and measure the distortion in a device-independent way. Wow, I mean, that's hardcore.
If we were, I mean, just to say, it's maximal when it is maximal entangled, but if it is a product state, what is the still maximum indefinite causal order is 1, 0.
There's no indefinite. If you have a product state in this setup, there's no indefinite anything.
It works.
Oh, it's always classically explainable, because it becomes a total order, so it's classically explainable. You must have non-locality. That's the comment you made yesterday. It must be non-local for you to be able to prove something. Indeed, if you don't, if you don't impose non-locality, then you can never get anything which is not classically explainable. There's always some hidden variable model that sort of propagates the information forward in a nice way. So it's the non-locality that gives you the inexplainability.
In a way, this argument, it has some connection to contextuality in some way.
Yeah.
In some way,
it does.
It's a byproduct of.
Yes, it does. But here you have, and I can go over the details more in the afternoon maybe. But here you have a specific choice of cover, if you will, a selection of measurements that have to be compatible. And in this scenario, you're only asking for the usual ones where each party, their inputs can be taken independently, if you will. So you're not putting any additional constraints, such as some of these must commute, or so technically this is a this is a very much non-locality argument. And maybe of interest to you, because you mentioned Leggett-Garg, is that here is Leggett-Garg. Sorry, I have to, yeah, I saw the words pass on my screen. That's Leggett-Garg. So that's the experiment by Leggett-Garg. That's the one that they present originally, where they have, see you later. They have, effectively, they have 3 measurements and they have some rotations in between. They start with a plus state. They perform the evolution of the system in the interval of time between each measurement is a y rotation by 2 pi over 3. If you sort of go and read how they how that system evolves. That's the degree of freedom that I care about. And then you measure, you have a control measurement. So either you choose to measure it in the Z basis or you don't measure it at all and you have zero outcome. So that's what their experiment does. It's a sequential experiment. And so it turns out that there is no contextuality in this experiment. There is no non-locality in this experiment. It is perfectly classically explainable. You can write the table of probabilities and you can prove that this is classically explainable. But what's happening is that if you look at the macro realism assumptions, what they are talking about really is they're asking for the model to be supported by 3 different causal orders. So they're not talking about contextuality, they're talking about causality. They're saying, I want I want A and B to be independent from C. I want B and C to be independent from A. I want A and C to be independent from B. And that's just a question of causality. So you're asking, can it be supported by the 3 causal orders below? And it turns out it can't, of course. And the violation that they observe is that comes from the fact that it is not supported by all of them. It's supported by the left one, of course, because the C measurement is the last one you did. So the C measurement, the A and B outcomes are independent of C. That's normal causality, but both A and B depend on, both B, C, and AC depend on A and B respectively. So there's only 56% and 62.5% support for the other 2 orders, and that's their violation. The violation is just the violation of causality. They're just saying our macro realist interpretation of this experiment is a requirement that this experiment should have a much stricter causal structure than it does. So we imagine. No, should I? Yeah, probably. So you can work out what the equations are exactly the equations for these 3 causal orders.
But you're saying then that this test of macrorealism is just an issue about causality.
Well, it is an issue about causality rather than an issue about contextuality or non-locality. Yes, contextuality. Yeah.
Yeah, no, but before was about macrorealism.
Yeah, it's not Sorry, Tony would be Tony Leggett. I never met either. I don't even know that. Are they here? Is Tony Leggett?
No, Tony Leggett is Rowan Champagne.
Oh, well, see, close, quite close. Okay, great. That's.
No. Tony is 85. Well, it's no, but it's not that. It's exponential when you're.
But see, their original point was about macro realism, and the entire argument is all perfectly. I mean, it's all correct. It's all valid.
I mean, we are thinking about doing with neutrons. So, but you're telling me now that with neutrons, what we are going to see is causality in the end.
Because so the thing is, for many years, at least in the specific field where this research was started, so the Abramsky-Brandenburger framework for non-locality and contextuality and the shift theory work on this, lots of people tried to figure out how to interpret the Leggett-Garg argument in terms of some form of contextuality in time. That was a question. It was an open question for a while. And so part of this, the work that we did with Nicola was answering that question as well. So we figured out, we looked at the equations from the point of, after knowing what the equations of causality look like in this setup, and it's just causality, there's no contextuality involved. But it's an interesting requirement of causality. It's the requirement that causally each outcome should not affect the other 2, which is each input, should not affect the other 2.
And you do not satisfy this kind of thing. I mean, suppose that you do an experiment.
Yeah.
And you do not violate.
That means that your operations were non-disturbing to the dynamics of the experiment. That's what it means. It means your measurements were commuting with the dynamics. And if you violate, it means that they are disturbing. That's what the Leggett-Garg argument proves. It proves that there are measurements that are disturbing they don't commute with the dynamics of a system, which for a classical system is a bit odd. Actually, for a classical system doesn't happen.
So the principle, you would expect that the measurements are disturbing this.
In quantum today, yes, but at the time, not necessarily.
In a certain sense, the only thing you're proving is that you are disturbing your system.
Yeah, you're proving that your measurements are not non-disturbing. Yeah, that's all or they are non-disturbing. They are disturbing in a certain way, in a certain pattern. But yeah, that's what you're proving. Nothing else. There's no contextuality involved in this. And even if it were, contextuality is arguably not a device independent notion, because you're putting your own knowledge, your own expectations about the commutativity of something, and that is not device independent. I mean, we have arguments about this. I say it's okay to say it's device independent in the sense that that part is, anyway, some stuff you have to put onto the experiment. You know some stuff. It's not that you don't know anything. You know what the outcome system is. You know what the inputs are. You know a few things. So you might as well include that information. Nicola is of the opinion that the contextuality is evil, and it's at least in part a device-dependent notion, because in a sense you're saying these two parts, I know something about them in the form of I know that they should commute, or I know that they should be compatibly definable, which is knowledge. To be fair, if you didn't know that the thing was quantum and you didn't know that the measurements were in a commuting basis, you wouldn't be compatible basis. You wouldn't be able to tell. You wouldn't be able to impose the constraint from the start that these are compatibly measurable. And so there's something else that we need to figure out there. There's some information that comes from experiments that tells you that that's true without looking into the box. And I think we have some stuff from a diagrammatic perspective that explains it, but not yet. So I don't know how to answer that question with boisterous certainty. I can give some guesses, but. Oh, okay. Which paper? This paper. Oh, okay. Wait for the abridged version to come out in a few weeks. I'll send it to you because it's the third of 3.
Sorry?
This is the third of 3 papers. Each of them is 80 pages long. And yeah, plus the 200 pages of supplementary materials, but yeah, who reads those? It's a long, but the abridged version is shorter. So. Is in this paper, yeah. Yeah, the Leggett Garg is the only one that you cared, and you can read this. You can already go and read this. Yeah, it's quite. I mean, the Leggett Garg is a fairly nice and specific example.
So, in this language, how would you distinguish the causality in like a Lorentz invariant sense and Galilean indistinguishable?
No, because you don't care about what causality means other than the fact that if you discard the outcomes of something, you're looking at a few isolated points in spacetime in a causal order. Well, hang on. When you say Galilean, do you still include bounded speeds of information transmission or not? No.
What he's doing, I'm pretty sure is Galilean, because he is not doing the relativity.
No. No, I would say that this is necessarily relativistic, actually.
No, it's not, but I think in the way, I have to read the paper, in the way you are thinking, I think that you're using e to the minus I, h, t, whatever, and when the thing is moving in time, you are using that operator, right?
We're not even incorporating, we are compensating for time movement into the operations that you make. So these qubits are stable in time. Okay. They're not even evolving in time.
One experiment, you have to make an assumption about how the system is evolving. When Alice is doing something, you have to put a Hamiltonian, you have to do something.
Yeah.
When I'm doing something, you have to do something. And that there is an assumption that you make when you're saying what is that something, whether it's relativistic or not.
I see.
And he's asking you, I mean, for example, if we were to do this with neutrons, it's non-relativistic.
Exactly.
I see what you mean.
That should be, if it is non-relativistic, that should have a Galilean.
Okay.
Type of symmetry.
So
not a lot.
there is no assumption like that here, because, and I'll go back to the slides to answer that. As I mentioned on this slide, we work from the quantum information setting, and so we don't typically include the explicit time evolution into our model. So we say our perspective would be that this is what we get, and it is part of the box, the process that you have at D, to incorporate any time evolution in whatever format you want, whatever quantum operator describes the evolution of gamma and delta from their initial parts to Diane. That's where it lives. It lives at D. But of course, there are setups where you have where you have more complicated, I guess I'll continue from this in the afternoon, but where you have more complicated scenarios where the time evolution is entangling, and then you might want to put boxes in between, like this. And then that is slightly different. So you have A, B, C, D. So the most general way to do this would be to put a box in the scenario in the middle. And you can do that.
Symmetry doesn't only affect the dynamics, it also affect those state space. Like for example, like it does like go like
Yeah. You put whatever you want.
But okay, it is dealing with a finite dimensional space. Yes.
Or qubits or
Qubits or
Because if you bring up the
it's not like, but you're thinking that your state is some sort of wave packet or is something where you can define because of the transformations of space. There are space-time transformations. There are particular transformations you can apply that are symmetries in one framework. And for example, in the case of relativistic, you have Lorentz transformation. In the case Lorentz boost, in the case of non-relativistic, you have Galilean. Is not using any of it. Is not incorporating space-time. So in this thing, it's just analyzing causality, legal causality, without any space-time. There is no really space-time. There is time in some way as a parameter, but there is no space-time structure.
Well, there is, in the sense that you have a discrete set of points in the causal order, and in principle, if you took it to the dense limit, you would be able to reconstruct your manifold up to conformal equivalence.
Question for Sari GR.
So it's just, that's the reason why I asked you only, but the box itself has that type of programming. I mean, sometimes there's input and output.
Yeah. That's the part I didn't yet get to, but because I've not yet shown what this picture looks like when you do causality. But that was what this. I was starting to draw this picture to show that effect. I'll do it in the afternoon. But the boxes themselves have to be causal in some sense. They don't have to be in the sense that you're going to get a probability distribution that's not going to be causal. I mean, to me, I don't care. It's a recipe for something. If you want to post-select on something, you post-select on something. I don't mind. But that becomes, actually, you can do that from a process theoretic perspective. And let me remember to do this properly in the afternoon. But here's what happens. You can take some of these models where you say part of the stuff that comes out of the box is in a causal environment, and part of it is not in a causal environment and is sort of traced somehow. And what you're really doing is you're applying some weird operator, some weird super operator that gives some kind of semantics to what it means to do that. And you effectively want to interpret diagrams that are on causal orders that perhaps look like this. Where you have loops. And as long as your loops are kind of nice and isolated, you can sort of, in fact, let me do it properly. You can cut the loop somewhere. You have boxes here, and you want to draw their boxes. And there's some other boxes, and you have boxes that kind of twist in time because there's a CTC somewhere. And what you do is you say, I cut somewhere here. I write the same exact thing, but without the CTC, by opening it at the bottom and at the top of the cut. And then I say, these two parts are identified. And then I impose some conditions that say that I can pull things in the CTC from one end and they appear from the other. So my super operator has some symmetries. And this gives you, for example, Lloyd's model or Deutsch model. And the problem is that both of those models are not linear probabilistically. So you get the linearity trap, and it doesn't make any sense to say my I get probability distributions for outputs on inputs, and the world is weird. I mean, the world is very odd. I do not fully, I understand from a process theoretic perspective what it means. And it's actually pretty shocking that the Deutsch model, and again, in the afternoon, we can have a discussion about it, but the Deutsch model is causal. So it satisfies the rules of causality, even though it has CTCs. Outside of the CTC world, it satisfies the rules of causality. You can discard things and you can define local slices and everything is perfectly nice. But what you lose by introducing these time loops, at least in these frameworks, is you no longer, probabilities mean nothing anymore. So you can no longer be an operationalist or an empiricist, as I would prefer to say. You cannot be an empiricist about the world. You have to be you have to be a member of some large Hilbert space cult. And you have to be the Pope of the Church of the Larger Hilbert Space. And then you say, I don't care about probabilities and free will. I have no free will. The universe is a big soup that evolves and we're just here for the ride, and then it works. But you can't, I don't know, I find it hard to imagine that I do science in a world where I cannot talk about empirical data and probabilities. So while I'm not quite ready to reject it, I think recent discussions about this have led me to believe that incorporating closed time-like curves with any of these models is inconsistent with empirical reasoning. And if you cannot say, I do this and I get these outcomes with some probabilities, I mean, that's tough. I think that's much, let's say, that's much harder to accept to me than non-locality. I mean, non-locality seems a perfectly normal thing. It's okay. You can't know everything. Some stuff is random. Not good. The fact that I can't use probabilities, and I mean, that's hard to swallow. So we can go over some of these like diagrams over indefinite causal order, diagrams over CTCs in the afternoon. We can talk about a bit more about causality. Then. Yeah.
I think one right comment, I mean, you know, like, because this whole modality thing is linked to the, because we didn't do the math, I can say somehow. Right, because, you know, in high energy, they don't care about this, they always say, neutrino is superposition of all these math items. Right, but in ordinary quantum mechanics, you have the buffer, like, to say that you cannot have different math. And that's the result, the original group based on Galileo and Galileo. And so the question is, you know, in this language, can you specify, like, distinguish these two modalities in some sense that gives you the buffer rule, the bond experimental, because the proof is very hard to do. Why?
I have never looked at it. We can look at it. What I can say is that this particular approach is is agnostic to the underlying choice of processes. So if you have a process theory which has Galilean semantics and super selection rules of a certain kind, you just use that category or you restrict to those processes and you do your diagrams like that. You don't need to add anything to this kind of formalism. All you need to do is pick the right boxes in the right process theory. That's all. And there are process theories for all of the there are process theories for bosonic systems, there are process theories for fermionic systems with these super vector spaces or sort of super selected Hilbert spaces. It's just a matter of really picking what you put into the boxes more than anything else. The problem arises if you are in a setting like field theory, where you cannot presume that you really managed to keep your systems separate and that they didn't evolve, or that you can absorb their evolution locally because they evolve in an entangling way. Like you have a very big diamond where actually as the systems progress, they could get entangled. As they come close, they don't come close fast enough. And imagine like you send it on a rocket ship. And in principle, these two atoms could have long range interactions. Obviously they don't, I mean, most of the time they don't, but they could. And then you have to perhaps take into account that because they didn't travel fast enough, they could have had some entangling interaction on the way. And there you have to do something like this, where you have to take them both together. But again, you can always just absorb this giant entangling interaction in the end, this one in Alice, and it works. The only place where it doesn't work is where you have something like a diamond lattice, right? There you might have an entangling interaction that acts across these, and then you cannot absorb it in a single box. And so sometimes you do have to send stuff into the entangler, get stuff out of the entangler, something like that. But nobody really deals with these scenarios. There, you can, as in the framework is perfectly well defined, but it's a bit hard to just calculate with such a level of detail. But we have an experiment, a numerical experiment. I have to. In my world, when you say experiment, what you mean is you're doing some calculation in the Jupyter notebook. In your world, stuff blows up. So yes, we have some numerical calculations that we want to do, trying to explain in the Dirac model, in the Dirac cellular automaton. You can ask, what if I have this process and I pick some points in this giant diamond lattice, and I say at those points I perturb the field. So instead of having the usual unitary evolution for that particular point, I do something. I have an instrument, a small quantum instrument there. And you ask if I have only 4 or if I repeat them, and then I let the field evolve under the rules of the QCA. So only local intervention, but local to one space, truly to one space-time point or to a small region of points, but those points. How much non-locality do I get? Is there an area law for the amount of non-locality I can get? And you expect something like that, because each intervention you can make on this field is very limited. The evolution will spread it out in a fairly uncontrolled way. And whatever change you made, the marginal that you get far away from your original intervention is going to carry a small amount of information about what you did, because the unitaries are going to constantly sort of spread it out, and then you're going to look at it from a local perspective, marginalize away lots of degrees of freedom, and then you look at one little instrument and you're going to get almost nothing. And so we expect to find area laws for these things. We expect that there's going to be a dependency on the area of the diamond, and there's going to be a dependency on the area of the intervention. But in order to simulate that, because the direct QCA is so strongly entangling, we can definitely not assume that the particle just goes straight. We have to sort of simulate it with a big CPTV map in the middle. That the full diamond is very solid. It has like a giant map in the middle that sort of does the full evolution. And that is an example of these settings where you can't presume that you send the particle without any entanglement happening. It will happen at some point. So that's in itself interesting, I guess. I don't know. But these afternoon diagrams for indefinite cause orders, diagrams for CTCs, causality in diagrams, which is an interesting topic. Anything else that I'm forgetting? Yes. So I think we'll stop. I'll stop sharing now, because we are well over time.
Thank you. What's your schedule look like today? Are you leaving today?
I'm leaving tomorrow.
Okay. And do you have anything